Hey everyone, hello Sebastian.
Hi, Dimitri. How are
How's it
you?
going?
That's going good. Thank you.
Okay, great. Are you ready to show JavaScript and WebAssembly magic for C++
I am.
programmers?
I am. C++ and
Okay,
WebAssembly magic. Yeah.
okay, let's start and good luck with your keynote. Have fun.
Thank you. Thank you very much. Welcome everybody to my talk. Today I will present a tool which is called Typescripten that makes it easier to develop web applications in C++. But before I start showing you this tool, I want to share with you an experience I had when I developed a small web application. So usually here at ThinkCell, we are developing a product only in C++. But recently, we wanted to build a small extension to that product, which is a web application. Here you see the website of Tableau.com, which is a large online data visualization tool where people can build visualizations, for example, charts. And we wanted to let users give the opportunity to import chart visualizations from Tableau.com into PowerPoint when they have our PowerPoint add-in installed. So you see here Tableau, and the user has a Chrome extension, and he can click on a chart. And now our web application opens, and the user can map the data in Tableau to the categories, series, and values of a stack chart, for example. And now he switches to PowerPoint, and the chart he had in Tableau will be recreated in PowerPoint, and it will remain linked to the original data in the Tableau.com web application. So there it is. So that's a ThinkCell chart, which cannot do all the things that ThinkCell chart can do. So this is a very tiny web application. You saw it. It has maybe 1,000 lines of TypeScript code. It has a single interesting problem that we had to solve. So we get data in tabular format from Tableau. So each individual value is one row in our data set. And we have to transform that into the familiar tabular data format that I need to create a chart. And in order to do that transformation, I have to sort all the individual category values and the series values. And I have to make them unique. So I have to get the unique list of category and series values. And then I have to do a repeated number of binary searches so that I can put all the values into the correct positions in the data table. And my individual data points can be numbers, strings, or dates in this case. So that's the only interesting problem I actually had to solve. So I programmed that in TypeScript. And that turned out to be surprisingly difficult. So the first problem, how to sort an array in JavaScript. I looked at the documentation, and the documentation says, by default, sorting an array in JavaScript will convert all the elements into strings and will then compare their sequences of code unit values. That's very surprising if you're coming from C++. But okay, we can fix that. We can specify a custom comparator for our sort. The next sentence is even worse. The time and space complexity of the sort cannot be guaranteed. That's horrible. I cannot fix that without programming my own sort. For all I know, the JavaScript array sort could use permutation sort. And then when I tried to solve the rest of the problem, there was no algorithm to get a unique range of values from a sorted array. And there was no built-in binary search either. Now, the experienced JavaScript programmer might say, well, you just go on npm and look for a binary search module, and then you're fine. So I did that. I Googled for binary search on npm. The first result isn't actually binary search. The second result implements binary search, and npm tells me it's the solution of the highest quality. I looked into it, and at the very least, it has the very common bug that it would actually not work if your array is very large. So if you have very large array indices, that solution would overflow. So that's suboptimal, let's say. I would really like to program this in C++ because that would be very, very easy. So my data value would just be a variant of double strings and time points. I would have a vector of those values that I could fill with the result of my data query. And then thanks to the C++ range library, I can simply sort that vector and then get the range of unique elements. And on that range, I can do binary search. And I'm very sure that binary search has logarithmic complexity and does not overflow on large ranges. I would not only like to program this in C++ because the C++ standard library is very strong and very powerful, it's also the language I'm most familiar with. And last but not least, there might also be some code sharing that I would like to do between my little web application and our large main application. So what do we need to do to get a C++ application onto the web? We need three things. So first, we need to compile C++ so that it can run in a web browser. Then we would like to call JavaScript from C++ because we want to manipulate the DOM tree to create some output. We want to use the common JavaScript APIs just to manipulate the page. And then last but not least, we want those calls to JavaScript to be type safe because that's what we're used to from C++. We would like to have the compiler help us in writing a correct program. So what do we need to get C++ onto the web? Well, that's where WebAssembly comes in. And WebAssembly and its predecessor ASM.js are not new technologies. They've been around for quite a few years. So I found a number of talks only at one conference. So there are 1,000 other talks about them. So this is going to be the shortest introduction to WebAssembly ever. WebAssembly is a compiled and binary format for programs, which has been standardized and is supported by all major browser vendors. It's a very fast and compact binary format, which supports 4 low-level data types natively. And these are integers and floating point numbers in their 32-bit and 64-bit variants. And each web application, each WebAssembly application, runs in its own individual sandbox. WebAssembly module cannot interact with the environment by default, so in that sense, it's a very secure technology. It cannot call any functions of its surrounding browser environment unless these are explicitly specified. And even each WebAssembly module has its own private piece of memory, essentially an array buffer of bytes that by default belong to that memory, to that WebAssembly module only. Usually, WebAssembly is instantiated from and interacts with JavaScript. So here on the left, let's say we have our WebAssembly binary, which defines a function A. And on the right, we have the surrounding JavaScript world inside our browser that defines a function B. And now the WebAssembly binary, the WebAssembly module can declare that it would like to import the JavaScript function, and it would like to export its own function. And now these two can call each other. So WebAssembly can call function B, and JavaScript can call function A. And WebAssembly can also export its memory object to JavaScript. Now, an important limitation here is that function A and function B can only have arguments and return values which are valid WebAssembly data types. That means they are limited to integer and floating point numbers. You cannot pass JavaScript objects to WebAssembly and back again to JavaScript, for example. So this is how it would look in code. We define two functions for our WebAssembly module that specify what we want to do when the WebAssembly module encounters an error. We abort. What do we do on a Stack Overflow? In both cases, we just abort the JavaScript program as well. We build a little map of the function imports, and then we instantiate a WebAssembly module with the binary we have downloaded from somewhere and the list of imported functions. And on the resulting instance, we can call the functions that WebAssembly exports to JavaScript. And this very simple form of interaction between the two is thankfully very, very fast. WebAssembly also defines a standard text format that makes it very easy and convenient to debug pure WebAssembly programs. So here we have the WebAssembly text representation for the C string compare function. You see it takes two parameters, 0 and 1, so parameter 0 and 1, and these are integers, 32-bit integers. So in our C++ program, these are pointers to zero-terminated strings, of course. So here in WebAssembly, they get transformed to integers, which are of offsets into the memory object of the WebAssembly module. So having a binary format is not yet enough to get C++ on the web. We also need some toolchain and runtime support. And this is what emscripten provides. So emscripten is both the toolchain, which is essentially CLang, which has a WebAssembly backend, and a set of runtime functions that provide useful functionality to our C++ program. Emscripten, for example, has C++ interfaces that implement the simple direct media layer API, which provides access to input devices, allows us to render graphics and create sound. And if a program doesn't use the SDL, then Emscripten also provides C++ headers for the OpenGL API, which directly map to the WebGL API in browsers. And Emscripten lets us access the input event APIs that are provided by HTML5. And last but not least, Emscripten also gives us a small virtualized file system, so you can actually bundle your WebAssembly application with files, textures, input files, and you can read them as if they were on the disk somewhere, but in reality, they're all part of your application. So this is a great tool, and this has been super successful in getting some applications into web browsers. For example, games. So a game is a very self-contained application that needs little else but graphics output, sound, and access to input devices. And with Emscripten, you can get those to run in a web browser relatively easily. Okay, so we can get C++ onto the web, thanks to WebAssembly and Emscripten. How can we call JavaScript from C++? Well, we've already seen one way. We have seen that WebAssembly and JavaScript can import and export each other's functions and call each other. But these are limited to integer and floating point parameters and return types. Now, Emscripten provides another way to call JavaScript from C++. You can directly embed JavaScript code into C++ code if you surround it with that macro here. Here it is em as an int. So em as an int inside the braces contains JavaScript code that will be executed at that point in our C++ program. And in this little example, you can even see that we can pass values to that macro, to that JavaScript code, and return values from that piece of JavaScript code back to C++. But again, these are limited to integer or double return values. Emscripten also provides a more powerful solution, the so-called mbind API, which makes use of an object which is called just Emscripten val, short for value. And that allows us to translate JavaScript code pretty directly to C++. So here in that little example, you see that we are accessing the JavaScript audio context API. So first, we're accessing the global audio context object. Then we're creating a new instance of the audio context. Then we're calling the create oscillator function, and we set the type of that oscillation to triangle and set a frequency that should correspond to a nice and pleasant middle C sound. So that's very convenient because it's such an obvious translation from JavaScript to C++. But that API has a big problem here. You see, we're calling a JavaScript function, and we are passing the name of that function by string to the JavaScript world. So at this point in our C++ code, when that code is compiled to WebAssembly, the compiler only sees a string. And the compiler cannot check, does that function actually exist on audio context? What arguments does it take? Which arguments are required? And what's its return value? Does it actually return a val? Because we also specify the return value explicitly. So that's a problem. It effectively means that this API combines the two disadvantages of JavaScript and C++. First, it forces us to compile the code to WebAssembly, and that takes time, and it's often just annoying. And that compilation doesn't even give us anything. It doesn't give us the type safety that compilation usually gives us. So here is where we would like to have something better, something that helps us program, actually. So let's take a small look at how that Emscripten runtime is actually implemented. Again, those Emscripten functions that we can call from C++, from WebAssembly, are functions that are implemented by Emscripten in the JavaScript world. So we have some private runtime functions, mval new object, new C string, etc. These are implemented in JavaScript and do something like the following. So we have mval new object implemented in JavaScript, and that in JavaScript simply creates a new JavaScript object, an empty object, without any properties, without any methods. And it initializes a reference count to that object to 1, and then stores both that JavaScript object and that reference count in some data structure in the JavaScript side of the browser runtime. And then it returns a handle to that map entry to the C++ world. So the emval that we return here to C++ is simply an integer. It's an integer that somehow identifies a JavaScript object. Emval new C string works in a similar way. It receives as argument a pointer to a zero terminated C string. And now the JavaScript implementation would read the zero terminated C string at that address from the WebAssembly memory object. And it will read it character by character and then append each character to a JavaScript string. And then again, it will store the JavaScript string and a reference count in some map and return a handle to that object to the C++ world. And if you have those two things, then you can imagine you can build a function that just increases the reference count, just decrements the reference count, or calls a method on one of those objects. But again, the method name would be passed by string, as we have seen, and cannot be verified at compile time. But okay, we have seen how we can call JavaScript from C++. Now, how can we make that more convenient for C++ programmers? How can we make type-safe calls to JavaScript? So let me show you how that could look. So let me first show you, then I have not mocked the example. So you have an empty web page. I have prepared a little example, but I haven't faked it for you. So here in the comments, you see a small JavaScript program which just creates a text element on a website. And now I would like to translate that to C++. So how could that look? Well, I get the global document object, call create element, and create a paragraph, set that in a text, and say hello to the audience, make the font a bit bigger, and then don't introduce typos because I never find them in a live talk, and then put that thing on the website. Okay, let's compile that. Yeah, it takes a moment. Oh, we get a compile error. That's always embarrassing in a live talk. So what does it say here? Okay, that line apparently is wrong, font size 20, because what does it say here? It says, oh, we are calling CSS style declaration font size, and that does not actually take a double. It takes a union of either null for whatever reason or a string. If you don't know that, in CSS you cannot say the font size is a number. You have to specify it as a string, because it takes a unit as well. Good thing we had this compiler here to help us. That's the kind of mistake you do when you're not a web developer. Okay, so now it should work. Let's hope it does. Oh, that looks good. Okay. There you go. So what just happened? Oh, sorry. Well, you saw our tool in action, of course. So what does our tool do? Our tool is a compiler that takes interface definitions for JavaScript libraries, which are written in TypeScript from the internet, from somewhere, and compiles them to C++ header definitions. So you can use the type information to program type safely in C++ against a naturally not so type safe JavaScript library. So what are these interface definitions? How do they look like? this is one example. This is an excerpt from the type definition library for the standard JavaScript DOM API for the document object that I've just used. And you can see here, the document object extends from some other objects. It has a URL property, which is a string, and it's read-only. It has an active element, which is either an element, like an HTML element, but it can be null. It has anchors, which are collections of HTML anchor elements. And it has a title as well, which is a string and which is settable by the user. And TypeScript not only comes with such type definition libraries for the built-in JavaScript APIs, but there's an online repository where users can submit interface definitions for all kinds of JavaScript libraries. And the last time I counted, there were over 7,000 of them for very popular JavaScript libraries like AngularJS, Bootstrap, or in our case, Tableau.com. And TypeScript not only comes with those powerful interface definitions, but it also ships with a super convenient parser and resolver API that allows us to read those interface definitions and get all the parsed and symbolicated type information from those interface definition files. So this is how the simplest program looks like that analyzes a source file. We can simply create a TypeScript program from an input file, then get a reference to the parsed source file, and then we can iterate over all the top-level syntax nodes in our interface definition file. And we can check, is that node a function declaration, or is it a variable statement? If it is a function declaration, we can go down further and check what's the name of that function, what's the return type that that function has, what are its argument, its type parameter, etc. So we can use that API to translate TypeScript interface definition files to C++ header files that you can include in your project. And that's what our TypeScripten our TypeScripten tool does, which is published on GitHub. It allows you to write typesafe and make idiomatic calls to JavaScript libraries based on the emscripten runtime that we have already seen. So where in JavaScript you would maybe simply assign a string to the title property of the document, you have to write something a bit more verbose in C++, but essentially it's the same thing. You call the title setter on the document and pass a JavaScript string to it, and all these calls are type checked. So based on the TypeScript interface definitions, we build headers that look a bit like this. So this is very much simplified, but it's in the spirit of things correct. So we create interfaces that are based on the emscripten val object we have seen that allows us to make untype checked calls to JavaScript. And then we essentially create a typesafe wrapper around that emscripten object. So here for the document, again, we know that the document has a title property, we know that returns a string, and we know that title property is settable, so we can generate the setter as well. Now, when we have to parse one programming language and you have to translate it into another one, you have to ask yourself, do we actually have to support TypeScript in all its complexity? Because it's a very elegant language, but it's at its base as complex and as flexible as JavaScript can be, because it's meant to describe JavaScript with all of its features. So for example, this is valid TypeScript. So here we declare an interface A with a function, and that function has one argument. And the type of that argument is not specified. We only have specified the requirement that whatever A's type is, it must have a length property. So this would be relatively hard to translate to C++. We could use concepts to check for length properties, but in the flexibility that TypeScript has, we don't want to generate a million concepts just for all the properties we might encounter. So luckily, I would say we don't have to support all of TypeScript. We just have to support the common subset of TypeScript that is actually used in interface definition files. And a lot of that luckily maps very well to C++ features. In practice, for example, programmers might choose to write the same statement like that instead and define some type with a length property for us. this is much easier to translate to C++. That being said, our tool supports a lot of the TypeScript features already and is already very usable. It supports all the built-in TypeScript types, like any undefined, null, and string. It supports optional members, optional member functions. It supports type guards, which are a TypeScript feature, which is a mixture of a type check and a cast. It supports TypeScript union types, mixed enumerations in TypeScript. And we also support passing C++ functions and C++ lambdas to JavaScript as callbacks. So they're called back into the C++ world. And we also support generic types, which are, of course, a lot like C++ templates. As of a few weeks ago, our tool is now self-hosting, which means it understands enough of TypeScript so that we can compile the interface definition for the TypeScript API itself, which our tool uses, of course. So our tool itself is written using itself, so to speak. So that means that this little TypeScript snippet I've shown you before that essentially parses and analyzes a TypeScript program can simply be transformed to C++, and then it looks broadly similar. And you see here in the highlighted line that we here pass a C++ lambda to JavaScript, which will then be called as a callback from TypeScript here back into C++. So that's pretty funky, and I'll show you how that works in a moment. So when you're translating one language into another, there are a lot of interesting language features that suddenly don't work in the other language, and you have to ask yourself, well, how can I translate that? So one such example is that in TypeScript, the declaration order of my classes does not matter. So this is a valid piece of TypeScript where I define a type foobar, which is the union of foo and bar. But at this point, neither foo nor bar have been declared yet. So this would be invalid in C++, but is valid in TypeScript. And here the fix is very simple, of course. We just have to collect all the types that we find first and then reorder them in some meaningful way so that base classes go before derived classes, etc. And we have to emit forward declarations for a lot of those things. We also support TypeScript union types, as I've already said. And they are also a very interesting language feature, which is very different from C++ unions or C++ variants. So in TypeScript, a union does not have a discriminating enumeration value, so you can't find out if the stored object is A, B, or C. Instead, you can think of it as being all of those types at once, and then the set of properties you can access on that object is exactly the intersection of properties of A, B, and C, which is a bit confusing that the union type has the intersection of members, but so it is. And conversely, that also means that such an object of union type A, B, or C is constructible from any value that has the same members as those that are shared by A, B, and C. So here in that example, I create a completely unrelated class D, but it has the correct property. And in TypeScript, you can assign D to an object of type A or B or C. And what this shows and what this means is that TypeScript is not, of course, a statically typed language in the way we understand it in C++, but it is what is called a structurally typed language. So a type, the name of a type is irrelevant. What matters is what properties an object has. And every object that has the correct property, here, comma number, satisfies the constraint that it has the same type as any other type name with the same set of properties. So a type is defined by the properties. Let's put it that way. Now, how do we translate that into C++? C++, of course, does not support structural typing. We have type names and they mean something. But there are a couple of things that we can do that are still useful and correct in C++ and TypeScript. For example, we can say that a union type of A, B, or C can convert to all the common base classes of A, B, and C. That's certainly valid in both languages. We can also say that a union type ABC can convert to wider union A, B, C, and D, because that type will certainly have a set of properties which is small are all the same. And we can also say that a union of A, B, or C is constructible from anything that can convert to A, B, or C. Now that sounds at first like a very big limitation, but in reality it isn't, because programmers are very lazy. And what we typically find in interface definition files in practice is that programmers don't like to repeat themselves, and that also obfuscates a lot of the relations. So in the interface definitions, programmers often express relations using inheritance relationships, like in that case, and they don't repeat the same property 5 times. So this is something then that we can easily translate to C++ because it contains all the important type information the way it works in C++. So, and last but not least, I said we also support mixed enumerations, which are a TypeScript feature where an enumeration can have integer and string and double options. And this is something we support in C++ in an entirely different way. We emit a normal enumeration, a normal C++ enumeration. But what we customize instead is the way that enumeration will be marshaled to the C++ world. So we define a little template type that we look up when we have to marshal the enumeration value, and that contains a map, a static map. And that map will tell us, oh, funny enum foo has to be marshaled as a string, and bar has to be marshaled as a double value. And that's how we solve that problem. Now, here's the map. Now, I also said that we support functions, C++ functions as callbacks in JavaScript. I also have prepared an example to show you how that looks. So again, I have this little code example here, and you see it's a little website, which is a bit unorderly. I would like to clean this up, but the button doesn't work yet. So we have to implement that callback. Okay, I have a function prepared, which is the click handler that I would like to use. And what it does is very, very straightforward. It takes a vector of those JavaScript elements, and it collects all the div elements from the website. It iterates over them, and then it collects all of those which are not null for some reason in that vector. Then we sort the vector of our page elements using our thincell range library. So we sort them using a less comparator, and we compare them by their height. And when we've done that, we iterate over them again, remove them, and add them again in their sorted order. And then I would like to add that as the click handler for my button. Now I cannot write this. This on click here is a function pointer, and I cannot pass a function pointer to JavaScript. We have to create a JavaScript object somehow. And the way we do that is with, unfortunately, some code generation magic, where we have to use a macro. So let me take that, put it here, and then we do this. So I have a little macro which creates a JavaScript function callback. So it's in the callback. Its name is onClick. Its return value is any, and this is its signature, and we don't need this. Okay, so otherwise it's the same function. Let me check that again so I don't make a typo here. Okay, and then that internally creates a function object for us. So let's go into that example and build it. That should work on this first try. I have not prepared a little error here. While that is building, let me show you how you can integrate our tool. So we use cmak here. And what you can do, or what you can do in your project, is you can fetch our Typescripten tool from GitHub and include a little cmak helper that we have written. And that exports a function that lets you say, okay, I have something, I have a Typescripten library, here the DOM library, that I would like to be translated to C++. So just pass it to that function. Tell me what the output is supposed to be called like. Tell me what target I should build it for. And that's it. And you have to set up emscripten, of course. And then you can simply include the DOM library in your project. So did that work? That worked, of course. Now let me reload. And there you go. It works. And what's even better about it is that you can now even debug those things in Google Chrome. Here you have your C++ code, our C++ code. You can set breakpoints, and that should even be called. There you go. So this we built all those WebAssembly projects using dwarf debug symbols, and Google Chrome in its latest version supports debugging WebAssembly with breakpoints, with local variables, with everything. So it's relatively convenient as a programming tool. Okay, so how did that work? How do function callbacks work? So in JavaScript, functions are just reference counted objects, like all the others are. And that can make it very hard to write correct programs. So let's say you have some program state that you want to manage. You have your class, which in its constructor wants to create a button. It registers a click handler. So you say that button is something that is only visible temporarily. So you want to add that button and then later remove it again and remove the click handler. And so in your constructor, you create the button and you register the click handler. And now you would like to destroy that button at some point, and that destructor should remove the button. It should remove the click handler. And that is something that is very hard or practically impossible to do in JavaScript, just because all of those objects are reference counted. So there's no deterministic destructions for your button class. That means you don't have a destructor. That means you can't deregister the event handler. And even if you did, the actual event handler would be a reference counted object and could be called whenever if somebody holds a reference to it. And that makes it very hard to think about the states that your program can have. And the solution in C++ would be much easier. So we can actually program it the way we want to. We create our button in the constructor, we remove it in the destructor, that destructor will be called, and best of all, our callback will also be destroyed and can never be called again, simply because it is actually an object. So that is slightly ugly syntax, I admit, but it makes a state machine very, very simple, makes it into something that I can reason about. So what happens here in that member function macro? So I said we have to create a function object. And that function object is a little helper that we have written, which is a JavaScript function object with this function signature. And it's called onClick because that's what we named it. And this JavaScript function object helper receives two arguments. It receives a pointer to a C++ function that we have also generated, and it receives this pointer. And now it calls into JavaScript. It calls a JavaScript function and passes the function pointer and the this pointer to JavaScript. Then it creates the JavaScript function object that will be actually registered as a callback to our button, for example. That JavaScript function object captures the function pointer and the this pointer. And when it is called, it will pass them back into the C++ world together with the actual arguments of the call. And now that JavaScript function object has one other interesting property, one other interesting function. We can detach from it. So when our C++ object onClick here goes out of scope, it will detach from its reference counted function object that can live for as long as it wants. And that can still be called, but it won't call back into C++ anymore because there's nobody to call. And now this JavaScript function object will be returned to the C++ world, and it will be held inside this object as an emscripten value, like all other JavaScript objects are. So now when the JavaScript object is called, I said it calls back into C++. It calls a generic entry point, passes its function pointer and this pointer back to C++. And this generic C++ entry point has one single task. it can cast the function pointer to the correct signature and call it. And then we are back in our generated wrapper function. And that one has another important task. It knows the correct function signature for our actual on-click function. So it can unwrap the JavaScript arguments one by one and pass them individually into our actual function implementation, which was this. It just took one single argument, which was an event. So that's quite a state machine that is going on here. No, state machine was the wrong word, but you understand what I mean. Quite a machinery. Our tool also supports generic classes now. So that was something that was hidden in my presentation, my last code example, where we had a collection of elements here. So this is a template in C++. So it's a collection of JavaScript elements. And we represent that as a template in C++, of course. Generic classes are very much like C++ templates. So for example, array in TypeScript is templated on the value type, just like array would be or vector is in C++. And we can translate it as a template. Interestingly, generics in TypeScript can have constraints. So for example, here, our interface A can say that its type parameter T must be one of the valid values of that enumeration. There's also something that our tool already supports. We can translate that into a C++ template that has a non-type template parameter. There are a lot of constraints that those TypeScript generics support. You can, for example, also say that a type T should extend class node. That sounds very much like we should translate it as something like this. So we could create this enable if, this enable of template magic that checks at compile time if type T actually derives from node, and only then enable our class A. Again, here as before, these are not quite the same semantics, but they work well in practice. So here in TypeScript, this really just means that T must have all the properties that node has, versus here in C++, this actually means T must derive from node. But in practice, this is exactly what programmers would write. Okay, now I have another code example, the last one. Because I wanted to show you initially that we can not only use that for the standard DOM APIs, but we can actually use a lot of TypeScript interface definitions for JavaScript libraries that we find on the internet. So let's go to the last example. And let's say we want to access the Tableau JavaScript API. So we can download the TypeScript interface definition from NPM for Tableau. And of course, I've done that already before. And then we go to our project. And we can also reference that in our cmak file. So here you see I don't only compile against the DOM API, I also compile against the Tableau type definition, put it all in one header. And then we can program against the Tableau API and create a visualization. So that's Tableau visualization. Create a new one. Sorry. Okay. I have to tell it where to insert the Tableau visualization. And I have a element on my website, of course, that I've just conveniently named Tableau. No. And then I just have to tell it which visualization. So that should be correct. Keep our fingers crossed. Okay, that worked. So we can reload that. And now it loads the Tableau visualization, which is probably a visualization you have seen before in Russia, wherever you are. So that shows, okay, we can just download type definition libraries from the web and program against them in C++ using Typesafe C++. And that almost ends my talk, but well, it shows what our tool can do. Our tool Typescripten will be superseded eventually when the WebAssembly interface type proposal passes. That's a proposal that is meant to improve WebAssembly so that we can express higher level types in WebAssembly. For example, JavaScript types. And that would enable us to make calls to JavaScript libraries directly from WebAssembly without the intermediate emscripten runtime. But that tool is very early still in its development. That proposal is still in a very early phase, and it might take a while until that passes, actually. I also did a small performance test of the interfaces that my tool generates. So I made a small test where I make 1 million calls of WebAssembly to JavaScript. And I called a very simple JavaScript function that simply increments a number. And I wanted to compare all the 3 ways I have to call JavaScript from C++. So I use a simple function that I import into WebAssembly. I use the emscripten macros that I have to call JavaScript. And I use an interface I generated via our Typescripten tool. And the interface header looks like this. And you see it passes a lot of strings to the JavaScript side that need to be unwrapped in JavaScript, converted into calls. So I imagined that would have quite an impact on performance. Not that the performance would matter very much when I put a button on a website, but we're doing C++, so we want to our tool to be performant as well. And of course, in that way, the way I'm currently implementing it, it isn't very performant, just because this runtime overhead of the emscripten runtime is pretty big. So I think this performance impact is almost entirely due to all the conversions that we have to do from integers to objects, from C strings to JavaScript strings. So this is something that I would like to improve in the future, of course. And there are quite a number of challenges that are still open if anybody is interested. So this is an important generic constraint that we actually don't support yet, where we want to say, okay, T in C++ should maybe derive from element. This is something that we should be able to emit. And then there's also a very interesting feature in TypeScript, which is very common in the DOM APIs. So maybe if you have programmed JavaScript, you certainly know, when you specify an event listener in JavaScript, then the first argument is a string that says what kind of event you want to listen for. And so the TypeScript designers had to come up with a way to make that interface type-safe, where you can actually pass an arbitrary string. And they came up with a very clever way and transformed that into a special kind of templated generic function, where they say, okay, my first argument here, k, is a string. But we say, okay, let that string be one of the keys of a type only implemented for type checking. So that type has a click property and it has a key down property. So we can only listen for those 2 events. So okay, type has to be one of those 2 strings. And then even better, that event that gets passed into our listener callback will be a different kind of class depending on the string we passed earlier. And they solved that by making a lookup of that string on that type, and that returns the right-hand side type here. So click maps to mouse events and key down maps to keyboard events. So this is something that's very common in the DOM APIs that we also have to support. So please check out our tool on GitHub. Contributors are very welcome, of course. The cmak integration is pretty new, so if anybody has experience with that and likes to try that out, then feel free. And let me know what we can improve. And with that, I am at the end of my talk, and I hope you have a lot of questions.
Hey, Sebastian, thank you for your talk. It was awesome. So we have a few questions. The first one, why do you use JSstring, your template string, instead of passing string directly?
I mean, here in the examples. So this is already a JavaScript object. So we have to do a transformation at some point. So the emscripten API will do that transformation anyway. So we have to pass the string as a JavaScript object because that's all that we can pass. It has to be translated into a Java string eventually. And I think we just out of convenience decided we do it here on our side. I could pass, you are right that I could pass a zero terminated C string so that I could pass that, but then somebody else would have to do that translation. So it doesn't really matter. I think for simplicity, we decided to create the string here on our end and generate easier interfaces. Otherwise, I think I would have to generate overloads maybe for get element by ID. That would have to have an overload for a JavaScript string. It would have to have overloads for std string and C string pointers, and they would all end up being the same thing. So we only generate that one.
Okay, then. So I've got a funny question to you. TypeScript has a type system, which is a
Mhm.
Turing complete, and you can write down a very strange things like parsing strings on types only in TypeScript. I mean, in ahead of time, like only by TypeScript. You mentioned a tricky solution related to the extends k off in the last few slides, and there are a lot of different things like conditional types, infills, awaited. What things do you plan to support?
Well, I would like. So what I find is that, for example, the Tableau interface is super simple. It was super simple to translate because the API is simple, and it was, I guess, pretty natural how to express that in TypeScript that doesn't contain any magic. So it was easy to translate to C++. And so, but the deeper you go, so when you look at the deeper you go in the TypeScript definition of basic JavaScript features, the more complex the TypeScript becomes. So the description of the DOM API is already relatively complex because it has those key-off constraints, because it translated interesting JavaScript API. But there is actually a TypeScript definition of the most basic JavaScript types of array and map and all those things. And these contain a lot of these use a lot of special TypeScript features that we cannot translate yet. So things like array or map are currently implemented by us. So we have kind of bootstrap support for the most important JavaScript types. So in the end, of course, I would like to be able to parse the TypeScript description of those basic JavaScript data types. And if I'm able to do that, then I would be very happy. I don't think they use conditional types. Maybe they do. I think they use a lot of anonymous types, for example, and these I don't support as well. So where you have, I don't know, a function, and that function returns an object and it doesn't even have a name. It's either this function is either this object or, I don't know, this object. And so this is something that you find in the most basic JavaScript TypeScript descriptions.
Okay, thank you. Another question related. It will be a general question related to embedding web C++ application into the browser by WASM. So you showed a lot of examples with manipulating the DOM structure. And you showed that there is a types from the TypeScript, which probably converted from the VIP ADL or something like that. But there is a good question. What do you think about, let's take, for example, Figma. They use JavaScript only for few things. For example, header of the page, and that's all. The central panel done on top of canvas, and they render their whole C++ applications into the canvas without manipulating DOM structure from the C++ code base.
Yeah, you can. That's what you can do right now with WebAssembly. Simply render everything into a canvas. But very often that's not so convenient. I mean, the web application that we have, that I showed you here in the beginning, is really a simple web application. It is especially a web application because actually on the left I embed the Tableau things that you want to import so that I can access them using their TypeScript library, their JavaScript libraries. But this is something where you really want to create a web page because it's just very, very convenient. It's a very convenient renderer in a lot of circumstances. So I think there is a use case for doing what I'm doing here, and that use case has been very inconvenient so far. And that's, I think, the value of our tool.
Okay, an additional question related we talked about JSstrings. Probably you could have an explicit constructor for JScript. JSstring, oops, sorry. Probably you can show your code base or something like, which will be more easy to understand.
It has. I mean, the JSstring. I don't know if I find the code base now, but the string. I should find it. Oh, yeah, it's here. Of course, it has an explicit constructor that makes the JSstring constructible by anything. I think actually maybe I even have to create now that you mention it. Maybe I even have to create a std string, because that's what emscripten takes. Let me check. Where's the string? It is constructible by well, in the end, it turns out I always have to create a std string anyway. Okay. So yeah, in that case, you're certainly right that I could, now that you mention it, pass a std string right away, maybe. But still, I think I would need the overloads. I would need to generate 2 overloads.
And the last question before we will meet to the discussion zone, will be a similar general question related to supported features in WebAssembly. As I know, there are a lot of limitations, like WebAssembly still did not support garbage collection, problem with threads probably.
No. But that's a good feature. That's a feature I like, that it doesn't support garbage collection. I mean, that's why we're doing C++, just so that we don't have garbage collection. Because that was the argument I made about reference counted function type. It just makes everything so hard to think about. When is your object destroyed? Never. So you start programming the entire destruction of your objects yourself. So you have to clean up state where you don't have to clean up state in C++. That's something we like very much about C++. No garbage collection.
Was it the biggest limitation in WebAssembly, or a little bit more? For example, you meet another.
I think exceptions. Exceptions are one limitation. We in practice we don't use them much, but they are sometimes convenient. But it is a limitation. But I don't think so I think we almost never use exceptions in code we have written ourselves. It's just that some of the libraries we interface with, well, we use exception. The only case I can think about where we really program exceptions ourselves is in our own platform independent abstraction for doing file input-output. Because naturally file input-output can fail, because the file is not there or whatever, and then you have to handle that, and exceptions are an elegant way to do that. But the browser environment is so much more predictable. You cannot read files, for one thing. that I don't even, I can't even think of a lot of ways, a lot of places where we would use exceptions now. So we typically don't use them.
We are out of time, so thank you for your talk.
Thank you very much for having me.
Let's move to discussion zone. Everyone, feel free to join us and discuss everything about it.
All right, I will do.